Alright, welcome to Rational Functions Part 3. So far we've talked about 1 over x and 1 over x squared. We've talked about the vertical asymptotes, which for 1 over x is where the denominator is equal to 0. We have the domain is x is everything but 0, we get a vertical asymptote. But what about this asymptote on the x-axis? Where does that come from, and how do we find that for other functions, for other rational functions, without having to plug in a lot of numbers like we did for 1 over x? Well, it turns out that that is related to end behavior. And if you remember talking about end behavior with polynomials, remember that's what happens when x gets very large. So we can say when x goes towards infinity, when x gets very large. So if we want to know, this is called a horizontal asymptote, if we want to know what's happening with the horizontal asymptote, we look at the end behavior. Alright, so let's go back to the idea that a rational function is a polynomial over a polynomial. And if you remember our polynomial notation from 5.1. Remember, it looked a little bit weird, but we did introduce it. It looks like an x to the n plus, and then we follow in this pattern, a2x squared plus a1x plus a naught. Okay, so all of the a's are the coefficients, and our polynomial goes all the way up to x to the n, whatever exponent is n. Now q is a different polynomial, so we need to use different letters. So an is usually used first, and then b and m are used second. So we've got bm x to the m, all the way down to b2x2 plus b1x plus b naught. Okay, so that's a different polynomial, so it's going to have different coefficients and a different exponent here. Now remember degree. So we say p has degree m, p has degree n, and q has degree m. Remember, the degree is the largest exponent in the polynomial. So p has degree n, and q has degree m. Alright, now also remembering back to our polynomials, okay, when x gets very large, okay, so we're talking about x getting out towards the ends of the graph. So this is not telling us what goes on the middle of the graph. This is for x is equal to 10, 100, 1,000, a million, stuff like that. Remember, when x gets very large, a polynomial looks like its power function. Looks like its power function. Okay, so ax to the n, for example. Alright, so what happens if we have px over qx? What happens when x gets very, very large is it starts to look like an x to the n over b m x to the m. Okay, remember when we talked about this before, when x gets really, really, really big, these other numbers don't matter as much. The x squared, the x cubed, the constants, those don't matter as much. What really starts to affect the numbers is just the first term. So an x to the n for p, and bm x to the m for q. Okay, polynomials start to look like they're power functions. So our rational function starts to look like an x to the n over bm x to the m. We're just looking at the first one. Alright, so now what does this tell us about the graph? Well, we've got these power functions, but what does this really tell us? Well, what matters ends up being the degree. Okay, so we're looking at n and m. P has degree n, q has degree m. And there's 3 different cases comparing n and m. So if n is less than m, All right, if n is less than m, so the degree on top is smaller than the bottom. Okay, the degree on top is smaller. Then what happens is, when x starts getting really, really big, the number on the bottom gets bigger and bigger and bigger and bigger and bigger. Okay, you with me? So the degree on top is smaller, so the degree on bottom is bigger. So this exponent is bigger, m is bigger. So x to the m gets bigger and bigger and bigger relative to the top. So what happens when the denominator gets really big? Think back to 1 over x. When the denominator gets bigger and bigger and bigger, we get closer to 0. So what happens is, when the degree on top is smaller, then the denominator gets bigger, which means the whole thing gets closer and closer to 0. Then, so what we say is, if n is less than m, then the graph has a horizontal asymptote at y equals 0. Okay, just like we saw with 1 over x, we end up with a horizontal asymptote at y equals 0. These numbers out on the end, when x gets bigger and bigger, are going to get closer and closer to 0. Okay, what happens if the degrees are the same? Well, if n is equal to m, then no matter what we put in there, the x's are going to cancel out. Okay, so if all of these other numbers don't matter and the x's cancel out, then what happens is, we say the horizontal asymptote, HA, okay, everything is going to cancel out. X to the n over x to the m, those are n and m are the same, those cancel out. So what we end up with is an over bm. We end up with just the leading coefficients. Okay, everything else cancels out, and what we get closer to, what our horizontal asymptote is an over bm. All right, and then our last case, if n is greater than m, if the degree on top is bigger. Okay, so the degree on top is bigger. So as x gets bigger, the number on top gets bigger and bigger and bigger and bigger, while the whole thing is just going to keep getting bigger and bigger and bigger. We never get closer to anything. We're just going to keep going up and up and up and up, kind of like a parabola maybe. All right, so if n is greater than n, then there is no horizontal asymptote. All right, now you can get something called an oblique asymptote from this, and the book does talk about oblique asymptotes. We are not going to cover that, so anything in the book where it talks about oblique asymptotes, you can read that on your own, or you can just go ahead and skip it, because we're not going to cover that right now. Okay, so let's look at a couple of examples of this so we can understand what's going on. All right, so let's say we have y is equal to 1 over x minus 4. 1 over x minus 4. Okay, so we need to look at the degrees first. Okay, so we've got our 3 cases over here, and we need to know what the degrees are. Okay, so what's the degree on top? We haven't actually talked about one like this, but if you remember, anything to the 0 is equal to 1. So any constant number goes with x to the 0. So any constant number is going to have degree 0. It seems a little strange, but the top is degree 0. Okay, the bottom, the largest exponent that we have is a 1, and so this is degree 1. So the degree on top is less than the degree on the bottom. This is case number 1 right here. Let's go ahead and, there's no set numbering for this, but I'm going to go ahead and number them just so we can refer to them. So case 1, case 2, case 3. Okay, so the degree on top is less. That's case number 1 right here. And we automatically have a horizontal asymptote at y equals 0. All right, let's say we have 2x squared plus 1 over x squared plus 3x minus 2. All right, so we're looking for horizontal asymptotes here, so we're looking at the degree. So the degree on top is 2, the highest exponent that we have is a 2, and the degree on the bottom is 2. Okay, so we see that? So degree on top is 2, the degree on the bottom is 2. Those are the highest exponents that we have. All right, what happens if the degrees match? That's case number 2 right here. If the degrees match, then we are looking at the leading coefficients. So this number over this number. So our horizontal asymptote is going to be 2 over 1, or just 2. Okay, and then our last example, let's say we have x cubed minus 3x over x plus 4. Okay, so the degree on top is 3. The degree on bottom is 1. Everybody see that? Degree on top is 3. Degree on bottom is implied to be a 1. So the degree on top is larger than the bottom. That's case number 3. If the degree on top is larger, then there is no horizontal asymptote. Okay, so no horizontal asymptote. All right, so that's how you identify the horizontal asymptotes. You look at the degrees, and you decide which one of these cases it is. Is the degree on top less, the same, or more? Okay, so in the next video, we're going to put all this together and see what this looks like on the graph.